Hi everyone, in this video we're going to be learning about conditional probability and the general multiplication rule. So we're going to start with computing conditional probabilities. A conditional probability, it's denoted like this, and the way you would read this is you would say the probability of, and then what's in parentheses is the event F given the event E. So the first event is listed first, so you're calculating the probability of that event given the second event that's listed after this vertical bar. So it's the probability that the event F occurs given that the event E has already occurred. So basically what's written second has occurred already, and then you're saying based on that, what's the probability of this other event occurring? So let's look at this example. Suppose a single die is rolled. What is the probability that the die comes up 3? So let's suppose that the die is rolled a second time, but we're told the outcome will be an odd number. What's the probability that the die will come up 3? So the first roll can be anything 1 through 6, because those are the 6 sides to the die. And so the probability of rolling a 3 is just 1 out of the 6th, or 1/6. The second roll, knowing that it's going to be odd, then our options are rolling a 1, 3, or 5. So in that case, read this as the probability of rolling a 3 such that the outcome is odd. And so that's just 1 out of the 3 odd options. So notice that the conditional probability reduces the size of the sample space under consideration. In this case, it went from 6 to 3 outcomes. So here's our conditional probability rule. So E and F are any 2 events. Then the probability, so this is the calculation for it, that we have a event F given that E has occurred. You can compute it as the probability of event E and F, so the intersection of the 2, divided by the probability of just event E. The other way to compute this is saying that the number of outcomes of events E and F divided by the number of outcomes in event E. So the probability of event F occurring, given that the occurrence of E already happened, then it's found by dividing the probability of E and F by the probability of E, which is exactly what we had right here, or by dividing the number of outcomes of E and F, which is what we had here, by the number of outcomes of E. So let's look at this one. In this table, the data represents the marital status and gender of the residents in the U.S., ages 15 and older, in the year 2017. So we have from never been married to separated, we have our total down here, and we have males, females, and then totals. So we're going to compute the probability that a randomly selected individual has never married given the individual is male. So remember, what's given, that's first, and then you're calculating the probability of this other event. So we're going to say given that they're male, we want to know the probability that they've never been married. Okay, so using our formula, remember how to read this. The probability given that the person is male, they've never been married. Okay, and so our computation is the number of outcomes in the intersection of male and never married, and then we just divide that by the number of outcomes of male. So from our table, the number of males that have never been married was 46, and then the total number of males was 126.9 for a total of 0.362. So the probability that the randomly selected individual has never been married given that they're male is about 36%. Now let's compute the probability that a randomly selected individual is male given the individual has never been married. So this is exactly the opposite of what we just did. The given part is that they've never been married, and now we're trying to see the probability that they're male based on that. So things are just switched. So probability that they're male given that they've never been married, and so we take the number of outcomes of male and never married, divide it by the number of outcomes of never married. So our numerator was the same because it was the intersection of male and married, never married, just like the last part A, but the denominator changed. So now we get about 53%. So the probability that the randomly selected individual is male, given that they've never been married, is about 53.4%. Let's take a look at this one. Suppose that 12.7% of all births are preterm. The gestation period of a pregnancy is less than 37 weeks. That's what preterm means. So also, about 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. What is the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm? And we want to determine, is this unusual? Okay, so the given part is that they're preterm, so they're born with less than 37 weeks pregnancy, and we're calculating the probability of their weight being 8 pounds, 13 ounces or more. Okay, so using our formula, our numerator is going to be the intersection of their weight and the preterm conditions, and then our denominator, the given part, was that they're preterm, so we're going to divide by that. So based on our percentages that we know from the given information, remember it was 0.22%, so when you change that to a decimal, that becomes 0.0022. So that's our numerator. Our denominator was 12.7%, or 0.127, so we get 0.0173, which is pretty small. That's about 1.7%. So if 100 preterm babies were randomly selected, we would expect about 2, because about 1.7, we just rounded up to 2, about 2 of them to weigh 8 pounds, 13 ounces or more. And so because it's such a small amount, 2 out of 100, we can call this an unusual outcome. Now let's compute probabilities using the general multiplication rule. So the general multiplication rule says that the probability that two events E and F both occur can be found by saying that it equals the probability that event E occurred, and you multiply that by the probability that event F occurred given that event E occurred. Okay, so let's take a look. So the probability that a driver who is speeding gets pulled over is about 0.8 or 80%. The probability that a driver gets a ticket given that he or she is pulled over is about 90%. What is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? Okay, so we have what we're looking for, our probability of a driver who is speeding gets pulled over and gets a ticket. And so it's the probability of two events, the overlap of them, so events E and F. And so using our general multiplication rule, we want the probability of the first event, which was driver who's speeding, times the probability that the driver gets a ticket given that they were pulled over, which is about 90%. So we get about 72%. And so the probability that a driver who is speeding gets pulled over and gets a ticket is 72%. Now suppose that 100 circuits sent to a manufacturing plant, that 5 of them are defective. The plant manager receiving the circuits randomly selects 2 and tests them. If both circuits work, she will accept the shipment. Otherwise, the shipment is rejected. What is the probability that the plant manager discovers at least 1 defective circuit and rejects the shipment? So of the 100 circuits, 5 are defective, so 95 are not. Okay, so one way we can approach this, we're going to construct a tree diagram to determine the possible outcomes for the experiment. So we're going to look at the figure, and then we're going to say D stands for defective, G stands for good or not defective. Okay, and so the outcomes are not equally likely. We'll include probabilities in our diagram to show how the probability of each outcome is obtained. And so this is done by multiplying the individual probabilities along the corresponding path in the diagram. All right, so let's take a look. The first circuit is pulled, and so it could be either good or defective. And so let's say it was good. 95 out of 100 of them are good, so that's the probability that the first one was good. Let's say the second circuit was pulled, and it was also good. Well, there's only 99 left, and we took out one of the good ones, so then that probability is 94 out of the remaining 99 are good. Okay, so the probability that both circuits were good is the product of the 2. So this second one here, this is saying the probability that the second circuit is good given that the first circuit was good. So that's why we're multiplying using our general multiplication rule. So that overall probability is about 90%. So So let's just look at another one. Let's say that the first circuit was defective, which is 5 out of 100. And let's say that the second circuit was also defective. So if we already took 1 out of the bad 5, then there's only 4 left, and we got 1 out of those 4. So the probability is 4. We could choose 4 out of the 99 remaining, and that's defective. And so that probability is the product of those two, and that would be a very unlikely event, but it's 0.002, or about 0.2%, that both are defective. And so the question was, what's the probability that at least one was defective? And there was 3 situations where that happened, where one was good, one was bad, one was good, one was bad, and they were both bad. So that's at least one being defective. It could occur any of these 3 ways. So we add up those individual probabilities, and we get that the probability that at least one was defective is about 9.8%. So the probability that the shipment will not be accepted is about 9.8%, or almost 10%. Now, another way to approach this is to compute the probability that both circuits are not defective, and then use the complement rule, which we've learned in the past, to determine the probability of at least one defective. Okay, so at least one defective, using our complement rule, is 1 minus the probability that none are defective. Remember, these are the complements. They have to add up to the total. The opposite of at least one defective is none defective. Okay, so what we're going to do to figure out this part here, we're expanding the probability that none are defective right here. And so notice it's still the 1 minus, so we continue that right here. But we expanded using our formula. The probability of none defective can be calculated as the probability of the first one not defective times the first one not being defective, then neither is the second one. Okay, so we still have our 1 minus, and then the first one not being defective we know is 95 out of 100. And then the second one not being defective, given that the first one was also not defective, was the 94 out of the remaining 99. So we multiply first, and then we have 1 minus 0.902, so 0.098, or about 9.8%. Same answer, just a different way to get there. Okay, let's take a look at this one. In a study to determine whether preferences for self are more or less prevalent than preferences for others, researchers first asked individuals to identify the person who is most valuable and likable to you, and your favorite other. Of the 1,519 individuals surveyed, 42 had chosen themselves as their favorite other. So let's do first, suppose we randomly select one of the 1,519 individuals surveyed. What is the probability that he or she chose himself or herself as their favorite other? So the probability that they chose themselves, well, it was 42 out of the 1,519, which is about 2.7%. So next, if 2 individuals from this group are randomly selected, what's the probability that both chose themselves as their favorite other? So this was that 1 chose himself, 1 randomly selected person. Now we're looking at 2. So we want the intersection of 2 events, where event 1 is 1 person chose himself, and then given that 1 person chose himself, the next person we randomly select also chose themselves. So using our general multiplication rule, we have the probability that the randomly selected person chose themselves as their favorite times the probability that given the first person chose themselves, so did the second person. And so we multiply. We already figured out the first probability. We multiply that by our conditional probability that out of the 42 people that selected themselves as favorite, so now there's only 41 of them left, and out of the total sample, there's only 1,518 people left. So we multiply, we get 0.0007, so that's about 0.07%. Now let's compute the probability of randomly selecting 2 individuals from this group who selected themselves as their favorite, assuming independence. Okay, so the assumption of independence means that the outcome of the first trial of the experiment does not affect the probability of the second trial. Okay, so basically it's always just the 42 out of the 1519, because if both the events are independent, exactly like it says, think of it as replacing. We have our 1,519 people. We can select any of the 42, and then the next person, we kind of like put that person's name back in the list so we can reselect out of 42 out of the original sample size. So that's when they're independent events. Okay, and so the probability that we still select 2 people from the group, but not conditionally, not assuming that the first one was selected themselves as their favorite, and then because of that, so the second person selected themselves as their favorite. So that rule was our general multiplication rule for independent events, which we learned previously. So that's just the individual probabilities being multiplied. So notice we didn't have to take away 1 from the total sample and take away 1 from the 42 as well. And so it's just changed our number slightly, 0.00076, or about 0.07%. So if small random samples are taken from large populations without replacement, it's reasonable to assume independence of the events. As a rule of thumb, if the sample size is less than 5% of the population size, we treat the events as independent. So if we're working with a sample size that represents a very small percent, 5% or less, than the whole population size, that's when we can say the events are independent. And so 2 events, E and F, that are independent, they're independent if the probability of event E given event F occurred is just equal to the probability that event E occurred, or exactly the opposite. The probability that event F occurs given event E occurred is the same as just probability that event F occurred on its own. So if 2 events are independent, you basically don't have to think about the conditional probabilities. You can just say the individual probabilities is what you're looking for. All right, that's it for this one. Thanks for watching.